This particular PowerPoint relates to chapter number 3, the AMS Weather Studies Introduction to Atmospheric Science, and it deals with terrestrial and solar radiation. One of the things that we have to appreciate about weather is that for weather to occur, there has to be energy, and there has to be an inflow and outflow of energy from the Earth's atmosphere systems. And what we also know is that the sun is the primary source of energy in our particular system. And the question we ask is, how does this affect us being a habitable planet? With over 200 billion stars in our particular solar system, the Milky Way, and with of those 200 billion stars, many having planets surrounding them, what is kind of unique about the Earth and its energy source, the sun, in terms of keeping our planet habitable? To answer that question, we have to really delve into this chapter and talk about things like electromagnetic radiation, the Earth atmosphere system, the conversion of solar energy or radiation to heat, Earth emissions as far as infrared radiation is concerned, and something known as the greenhouse effect. We'll be discussing these in the next few slides. We have known for obviously a long period of time that there are recurring patterns of seasonal change, and that has obviously been important to individuals living in those ancient times, as evidenced by specific astronomical calendars which they have produced. The next two slides show a little bit about the history of these specific astronomical calendars and where they exist. Since we do know that the sun is the main source of energy, we have to know something about what type of energy the sun relays to the Earth system. We have to talk about that in terms of something called electromagnetic radiation, and that has some very specific properties, including the fact that this radiation from the solar system and the sun itself has both electric and magnetic properties and is transmitted through space in the form of waves. Now, waves always have two things, a wavelength and a wave frequency, and this particular diagram gives us the indication of the difference between those two. The speed of this radiation is about 186,000 miles per second, which we commonly call the speed of light. One of the things we should appreciate is that wave frequency is inversely proportional to its wavelength. That is, the higher the frequency, the shorter the wavelength. Radio waves have frequencies that are very, very large, and this next slide shows us the relationship between the frequencies, their wavelength, and where these different types of spectra are found, from long radio waves up here at the top to very, very short and highly powerful gamma rays, X-rays, and UV radiation found in the lower part of this spectrum. Notice that visible light is found just above the UV and just under the infrared radiation, and these are all the visible spectra that our eyes have the ability to interpret in our brains. Because radiation is a natural phenomenon, it obviously has to follow natural laws, and these are called the radiation laws. There are several physical laws that describe the properties of electromagnetic radiation, and one of those is something known as a black body, and a black body is by definition something that at a constant temperature absorbs all radiation and incidence on it and emits a radiation energy that absorbs. A black body is therefore something known as a perfect absorber and perfect emitter. There are some real objects that may approximate black bodies for certain wavelengths of radiation, but not for others. Because we're interested in the sun and the earth in terms of our radiation, basically, although they are not perfect black bodies, their absorption and emission of radiation are close enough that we can apply black body radiation laws to them with relatively useful results. Some of the mathematical laws associated with this black body and other radiation components is something known as Wien's displacement law. According to this law, hot objects such as, say, the sun emit radiation that peaks at relatively short wavelengths, whereas relatively cold objects, that is, something like the Earth atmosphere system, emits radiation at longer wavelengths and lower frequency. As your book points out, the top heating elements of an electric stove are an illustration of Wien's displacement law. So look that over and see if you can make sense of that particular law as described. This particular slide deals with radiation laws relative to area under the black body curves. Again, this is a little bit more complex than you may want to know, but the total radiation energy emitted per unit time per unit surface area at all wavelengths is shown here. The problem is that the vertical scales in the two figures, one for the sun, basically solar radiation, and the other for the earth, are very different. According to the Stefan Boltzmann law, the total energy flux emitted by a black body across all these wavelengths is proportional to the fourth power of the absolute temperature. Well, what does that really mean? What it means is a small change in the temperature of a black body results in much greater change in the total amount of radiation energy emitted by the black body during a given time interval. What does that mean? That simply means that the sun radiates at a much higher temperature than the Earth's surface. So the Stefan Boltzmann law predicts that the rate of the sun's energy output per square meter is almost 190,000 times that of the Earth system to space. So basically the sun mathematically should be significantly hotter than the Earth, and it is. Another mathematical law for us to appreciate is something called the inverse square law. We know that as solar radiation travels from the sun and spreads out into space in all directions, its intensity diminishes, and it diminishes as the inverse square of the distance traveled. Well, what does that mean? That means, according to this law, doubling the distance traveled by radiation reduces its intensity to 1/2 squared, or 1/4 of its original initial value. So if we were to look at three planets, Venus, Earth, and Mars, we would find that Venus, being closer to the sun, receives nearly twice as much solar radiation per unit that is intercepted relative to the Earth. So Venus is way too hot for life, with surface temperatures ranging over 180-160 degrees Fahrenheit. Mars, which is farther away from the sun, has radiation less than 1/2 of the intensity that the Earth has, and is too cold for life, with surface temperatures averaging somewhere around -63 degrees Fahrenheit. Therefore, the Earth seems to be in the perfect place relative to distance from the sun to maintain living forms, simply by the fact that water is not continually frozen or evaporated because of too little or too much heat. So let's look at the sun for a minute and talk a little bit about this, since this is our basic energy source where the solar radiation is concerned. Basically, the sun is burning internally at somewhere around 20 million degrees centigrade. This solar furnace is basically formed by something called nuclear fusion reactions. This is where hydrogen form helium with the release of energy. The energy is used to bond various nuclei, and much of the energy is radiated off the sun's surface, then out into outer space, which we call the solar radiation. There are areas of the sun that are uniquely distinct, such as the photosphere, which is the cooler uh, than the interior. That's the visible surface of the sun. Sunspots, which are cool areas on this photosphere area, the surface of the sun. And the chromosphere, which is the atmosphere above the photosphere, and is composed mostly of hydrogen and helium with something called the solar corona, which are the outermost portions of this particular atmosphere. One of the important things to appreciate is that sunspots can often affect the Earth's climate, and we'll talk more about that later in a upcoming chapter. One of the things that affects the input of solar radiation onto the Earth is something known as solar altitude. That's nothing more than really the angle of the sun above the horizon, and this altitude influences the intensity of the solar radiation that is received on the Earth's surface. This demonstration in terms of the slide shows that obviously the greater angle of solar radiation, the more area the sun encompasses, and obviously the less heat in a specific area means that the concentration of the solar radiation in terms of its solar altitude will determine warmer or hotter ground temperatures. Even though we're 93 or so million miles away from the sun, and the sun probably reaches us in rather parallel beams, because the Earth is curved on its surface to this incoming solar radiation, noon solar altitude is always going to vary with the latitude. The intensity of solar radiation actually striking the Earth's atmosphere is greatest at the latitude where the noon sun is at its zenith, that is, solar altitude of about 90 degrees, and decreases with distance north and south of that particular latitude. This particular graph shows how the input of solar radiation is affected by various latitudes. Here is basically Singapore, which is pretty much at the equator. Here is Brockport, New York, which is just west of Utica by Rochester, showing you that there is a very different input of solar radiation throughout the year. And then the Antarctic has very, very unique kind of solar inputs throughout the year. So as we can see, the intensity of solar radiation striking surfaces over the Earth is variable, and it's due in many regards to the inclination of the Earth's axis. When the North Pole is tilted towards the Sun and Northern Hemisphere receives more of the solar radiation, that is generally in the spring or summer in the Northern Hemisphere. When the pole is tilted away from the Sun at 23 degrees or so, the Northern Hemisphere receives less solar radiation, and we call this fall and winter as far as the Northern Hemisphere is concerned. We also know that the Earth revolves around the Sun, and the Earth's motion in space, it brings about seasons. And there are a couple of terms which we will be using, and those are something known as the solstice, or the equinox. And June 21st, solstice, is when the sun is directly overhead the Tropic of Cancer, which is about 23 degrees north latitude. The equinox, and equinox means equal night, the sun is directly overhead the equator, and that's generally in the 23rd or so of September. And that's when we begin to talk about the Northern Hemisphere fall season. In December 21st, solstice, the sun is directly over the Tropic of Capricorn, which is 23.5 degrees south latitude, and that's the beginning of Northern Hemisphere winter. And then March 21st, the sun is directly over the equator again, beginning of the Northern Hemisphere spring. So the solstices and equinoxes are four different times during the year that we can relate to changes in our season. The next several slides give you some information regarding the equinoxes. And one of the things to notice in this particular slide is that the sun is actually closer to the Earth in December than it is in July, and this is when the summer solstice occurred, and this is the winter solstice, I'm sorry, and this is the summer solstice. The terms associated with this, the distance from the sun, are called the perihelion and the aphelion. So those are terms you may look over. In addition, these next few slides give us some other information relative to the solstices and the equinoxes, their paths in the sun at both the northern hemisphere, the North Pole, and at the equator. So look those over and see if you can appreciate what they're trying to tell us. The variation day length increases with increasing latitude, and this shows that in this particular graph, going from Canada down to Mexico City and Caracas, and shows you the duration of daylight during those time frames. One of the terms used as far as radiation is concerned is something called the solar constant. And this is defined at the rate at which solar radiation falls on a specific flat surface located at the outer edge of the atmosphere. And the constant designation is a bit misleading because solar energy output actually fluctuates, not by much, but it does fluctuate over the year. The rate of total solar energy input from the planet varies through the course of the year, basically from perihelion to aphelion. And since the Earth is about 3.3% closer to the Sun at perihelion than at aphelion, if we use the inverse square law, the planet intercepts about 6.7% more radiation at perihelion than at aphelion. So there is fluctuation to some degree of solar radiation. This particular slide shows the distribution of solar radiation received by the atmosphere, at the top of the atmosphere by latitude and day of year here, latitude here. Now we can see that there are several lines associated with that where latitude and longitude in relationship to solar radiation is very, very distinct. There are several things that can happen to solar radiation as it enters the Earth's atmosphere, and passing through the Earth's atmosphere with aerosols and gases and other things, there is basically three things that happen: scattering, reflection, and absorption. But what we do know is that within the atmosphere, the absorptivity, the scattering or reflected albedo, or the transmission to to Earth's surface, which is called transmissivity, has to equal 100%. This slide describes some of the things that go on with relative scattering and reflection. One of the interesting things is there is a preferential scattering of blue-violet light by oxygen and nitrogen molecules in the atmosphere. So this is basically why daytime sky is blue. In terms of reflection, uh, there are a number of ways that things are scattered, but basically the fraction of scattering uh, by airborne particles or reflected by the surface is known as the albedo of that surface. The stratospheric area of our atmosphere plays a very significant role in the formation of something called the ozone shield. Um, this area absorbs radiant energy and converts radiant heat to energy, and there are chemical reactions involved in the formation of a molecule called ozone, that is O3 as compared with oxygen, O2, and both of these are really strong absorbers of solar ultraviolet radiation, and we find that the net effect of absorption of this ultraviolet radiation is really twofold. There is a significant reduction in the intensity of the ultraviolet that reaches the Earth's surface, and secondly, a marked warming of the upper atmosphere. Uh, in addition to these two gases, also water vapor has the ability to absorb some ultraviolet radiation, and because of this formation of ozone and the other components, we form something called an ozone shield, which protects us from ultraviolet radiation, which can have a detrimental effect on living organisms, especially in terms of disrupting genetic materials found in living things. Although ozone is good for us in terms of the stratosphere, ozone at lower tropospheric areas can have a very detrimental effect on our health. So there's good and bad with ozone. This particular slide shows how ozone is produced and ultimately destroyed. This graphic displays the idea that there are a number of chemicals that threaten to destroy stratospheric ozone, and that is both from industrial and natural sources. Some are injected into the atmosphere during the volcanic eruptions or even in the exhaust of relatively high-flying aircraft. Additionally, ozone-destroying chemicals are transported from sources on the Earth's surface by relatively strong convective currents in the tropics that build thunderstorms and surge upward through the tropopause and actually into the stratosphere. These chemicals include things like chlorofluorocarbons, methane, nitrous oxides, and water vapor. Within the stratosphere, intense ultraviolet radiation breaks down these compounds to form radicals, which have an effect on destroying much of the stratospheric ozone layer. There have been many studies relative to ozone and its effects on atmospheres specifically in the Antarctic region, as we will see. This particular graphic in your text shows the ozone hole as it existed in September 24th, 2006. Probably the largest time we saw the ozone hole in terms of the millions of square miles that it covers. The blue area are low areas of ozone, while the yellow and bluish areas are higher concentrations of ozone. So in this particular area, we have lost our ability to take and absorb ultraviolet radiation, which that means that the very high energy electromagnetic component reaches the surface of the Earth and has deleterious effects on living organisms. The concept of albedo is extremely important, especially when we look at visible satellite images. We notice that when we do that, water surfaces appear black because of their low albedo. That is, the global oceanic average of albedo is 8%, which means that 90%, 92% of the solar energy reaching the oceans is absorbed. So the oceans are very, very good in terms of absorbing radiant energy. This albedo varies with solar altitude uh, and decreases rapidly as solar altitude increases. This graph in your text or table in your text shows you the albedo reflected, and notice how the water body are very percent reflectivity is pretty low, whereas things like sand, green crops, grasslands, fresh snow are significantly higher than we find out. The lighter the surface, the higher the albedo. Notice that the oceans are relatively dark, meaning relatively low albedo, absorbing much of the energy. This slide shows our global solar radiation budget. 30% reflected by the Earth's atmosphere system, 23% is absorbed by the atmosphere, and about 47% is absorbed on the Earth's surface. Obviously, we have to have the loss of some radiation, or the Earth would continue to heat up. So what we find out that much of the system is balanced by emissions of heat to space in the form of infrared radiation. We'll talk more about that a little bit later. The greenhouse effect refers to the heating of the Earth's surface and lower atmosphere caused by strong absorption and emission of infrared radiation by certain atmospheric gases, which are known as greenhouse gases. Whereas the sun emits ultraviolet and visible radiation, the Earth actually emits long-wave infrared radiation. The greenhouse gases that we're talking about, such as water vapor and carbon dioxide, methane, and others, are transparent to short-wave radiation but absorb long-wave radiation, which is what the Earth emits. Greenhouse gases have been given some bad press, but what we have to realize is that Earth really is kept warm by greenhouse gases, and without this warming effect, life as we know it would not exist. Our problem is too many greenhouse gases, which can bring about climate change, and that's our concern at this point in time. This particular graph gives us some indication about absorptivity as the fraction of radiation absorbed in ranges from 0 to 100%. Each of the specific greenhouse gases is listed, and you can see the absorptivity of each of those as far as the atmosphere is concerned. Guy Stewart Callender, who lived from 1898 to 1964, was the first to investigate the link between global warming and fossil fuel consumption beginning in the 30s, and the Callender effect is actually named after him, and this is a theory that global climate change can be brought about by enhancement of the Earth's natural greenhouse effect by increased levels of atmospheric CO2 from anthropogenic sources. That means from man-made sources of CO2. Systematic monitoring of carbon dioxide began in 1957 in Hawaii. It's obvious from this next slide from these recordings in Hawaii that the atmospheric carbon dioxide concentration is significantly increasing over the years from 1960 to 2010. This is going to increase our greenhouse gases, obviously, and the effect that they cause relative to global climate change. The same is true for another greenhouse gas called methane, and we can see significant rises from 1983 to 2011. The average growth of atmospheric methane is a bit fluctual because of some of the methane sinks or areas where methane can be stored on the surface of the Earth itself. Nitrous oxide, as we can see, another greenhouse component, is rising rapidly also. And one of the things that we can see is that the concentrations of carbon, fluorocarbons, is actually kind of leveling off, but there are still relatively high concentrations in the atmosphere because of their very long-lasting effect and lifespan within the atmosphere itself. So even though we're not using many, it is not decreasing nearly as rapidly as we would hope. These next few slides give us some idea about the impacts of global warming as climate zones shift towards the poles. We would find rising sea levels, decreased snow cover, and heat and moisture stress to crops, but there may be areas where crops are not growing now that there would grow, so there's possible farming at higher latitudes. Also, the annual average temperature over the long term, as we can see, is going to be significant, and that will bring about some very, very interesting changes in our climate. There's much agreement that we should take as much action as possible to prevent increased greenhouse warming, such as reducing oil and coal consumptions, greater reliance on non-fossil fuel energy sources, have more energy efficiencies, prevent deforestation, and bring about more reforestation, and in general cutting air pollution. The way that we measure radiation is by an instrument called a pyrometer, and it's a standard instrument for measuring the intensity of solar radiation striking on, relatively horizontal surfaces. It's a sensor enclosed in a hemisphere that transmits total solar shortwave radiation. And here's a picture of one that we can see that gave us some data from our friends in Brockport, New York. That's the end of this PowerPoint. If you have further questions, you can refer back to the text, which encloses or has all of these various components associated with the chapter. Thank you.